Hello. Hi, everyone. Thank you for the introduction, Ariana. My name is Lauren Sgro. I'm a postdoc at the SETI Institute. And today I'm going to talk to you about what everyone actually came to talk about, which is aliens, of course. No, in all seriousness, I'm going to talk to you about the LaserSETI project, expanding our search for extraterrestrial intelligence. But I know that not everybody may be familiar with what SETI is. So I work for the SETI Institute, but SETI as a whole stands for Search for Extraterrestrial Intelligence. We search for extraterrestrial intelligence across multiple different parts of the electromagnetic spectrum, namely radio, optical, microwave, and infrared. So electromagnetic spectrum right here in case you wanted to go back to your Physics 101 class. But we search for radio, for one, because it's easy to have ground-based telescopes that can actually detect things in space. Our atmosphere doesn't really interfere, although we have lots of technological stuff that can get in the way of searching for extraterrestrial signals in the radio. One of the reasons that we search is there's something called the 21 centimeter hydrogen line, and this is a really prevalent signal in the universe because hydrogen gets excited and it emits energy, and we see the signal at 1420 gigahertz, megahertz, it's besides the point, but we see this in the radio portion of the spectrum, and we think that maybe if extraterrestrials are trying to signal us, maybe they'll use that because it's prevalent across the entire universe. We search in the microwave as well. Similarly, it's easy to observe space from the ground. There are portions of the microwave spectrum that are pretty quiet as far as goes astrophysical processes are concerned. So there's not a lot of interference. Maybe ET would try to communicate with us there. Infrared is a little bit more difficult because of our atmosphere and the interference that comes with that. But if there are extraterrestrial civilizations out there that are generating a lot of heat, maybe a Dyson sphere used to harness energy around a star, then we may be able to see that increase in heat around a star or a planet or whatever these aliens are building, hypothetically. So there's a lot of different ways that we can search for extraterrestrial intelligence, and I'll talk to you a little bit later about searching for ET in the optical. That's what LaserSETI is all about. But before I do that, I want to give you a brief history of SETI. We didn't just come to this point and I'm sitting on the stage saying, let's talk about aliens, without a search that brought us to this place. SETI itself, the search in general, is fairly new, but probably older than you would think. This started in the early 1900s, where people had this idea that maybe we could use radio to search for ET. And it started to pick up steam in around the 1960s when certain scientists started to think, hey, what if we also searched in the microwave portion of the electromagnetic spectrum? And then in 1960, a scientist named Frank Drake, you may have heard of his name. Has anybody heard of the Drake equation? That would be him. And he actually is quite famous for conducting what's kind of like the flagship SETI search. This was the first real experiment that people think of when they say SETI started. SETI started here with Project Ozma, the Green Bank telescope in West Virginia. He was searching that 21 centimeter hydrogen line around 2 nearby stars, and he searched for a few months in the spring and summer of 1960, and he found something, but it turned out to probably be an airplane. But that's how the search started, is with some false positives, which is always good. That helps us know what we're looking for and what we're not. Then later in the 1960s, we had the Ohio State Big Ear Telescope. It does look like a football field, in case you were wondering. But this was a really prevalent search because it lasted up until the 90s. And this telescope was basically doing SETI searches all of the time. And you may have heard about the WOW signal. Does that sound familiar to anybody? So that was, someone said, yeah. So that was discovered by the Big Ear Telescope in 1977. It's called the WOW signal because the scientist who was looking at the data come in looked at they were observing around this 21 centimeter hydrogen line, and the signal that they got from this one particular night was really, really strong, many times above the background noise. And it was so strong that he circled on a piece of paper. This is when all the outputs were on a piece of paper, circled it, and put wow. And that's an actual picture of what he circled. That's why it's called the wow signal. We still don't know exactly what that was. It's never been repeated, but there have been some recent papers by some collaborators, actually, that address that and what it may have been. But in this time, NASA was starting to fund some cool SETI searches, namely the NASA Microwave Observing Program, I think started in the early 1980s, but then funding got cut, as it does. And we're in a similar place now, but that's okay, we'll make it through. And part of that inspired the creation of the SETI Institute, which I'll talk about more in just a second. But SETI Institute's doing its stuff, and then in the meantime, NASA restarts some funding to restart the Microwave Observing Program in 1992, and then someone at Congress noticed and was mad about it, which is a thing that happens quite often. But they noticed, and it was too much money, and they stopped funding the project. And that's when the SETI Institute really came into focus, because in 1994, the SETI Institute started basically to revamp the Microwave Observing Project, pick it up with private funding. And Jill Tarter was the one that led this, but they used private funding. SETI Institute was doing all of this instead of it necessarily being NASA funded. And it was, like I said, a continuation of this program, and this program actually lasted until the early 2010s, which is pretty cool. But they used Arecibo, fortunately, RIP, no longer in commission, to search nearby stars for signs of extraterrestrial intelligence. And didn't necessarily find anything, but that was an important hallmark in the search for extraterrestrial intelligence, that this is important and valued by the community, so much so that people will fund it, people will take on this work, even if it's not NASA funded. So that brings me to the SETI Institute today, which is where I work and several other people in this audience work. This is, like I said, founded in 1984 by Jill Tarter and the CEO of a company that I've now forgotten. I believe it was a copy company, maybe a printing company. But they had this vision to basically conduct SETI research, outreach, and education without all of the overhead that the government was bringing. And now we have over 100 scientists working for the Carl Sagan Center for Research, and Carl Sagan was originally on the board of trustees, which is why he's here. So that's your crash course. Thank you for listening. There's the whole history of SETI, and that kind of brings us to where we're at today, which is still asking this question of, are we alone? Are we alone in the universe? And there's a lot of different ways to investigate that question. And at the SETI Institute, we're not all just looking for aliens all the time. If we were, that would probably be really fun, but there's a lot of additional science that needs to be done. So we do have the Allen Telescope Array. That's how we look for ET signals in the radio. We also have optical SETI, which I'll talk about in a second. But we also look for signals of life in our solar system that would inform us of how to continue the search elsewhere. We also look at exoplanet demographics. We study exoplanets, we try to find them. If there's going to be life in this universe other than us, then where is it? We have to understand where we're looking at. So there's a lot of different things that the SETI Institute does, and one of them is actually looking for aliens. Now, I will get to the part that we're all waiting for, which is, what is optical SETI? What is LaserSETI? So, like I mentioned, we can search for extraterrestrial signals in radio, infrared, microwave. But what about the optical? Now, if we were doing an optical SETI search, what may we be looking for? There's a couple of different things that we've hypothesized. It could be possible that there's some communication that an extraterrestrial civilization is trying to make with each other, other civilizations. Maybe it's interstellar, maybe it's interplanetary. Could we perhaps intercept that? If they're using laser technology, space is pretty empty and lasers stay pretty coherent. They don't spread out a whole ton, so not really sure if that is something that we would be able to intercept, but it is a possibility. What about beamed energy propulsion? That is this idea that we could basically propel a spacecraft using laser light. So there was an idea called Breakthrough Starshot that kind of proposed this idea here on Earth to use a 100 gigawatt laser to propel small spacecrafts to a nearby star system by using that laser light to essentially propel the spacecraft close to the speed of light so it wouldn't quite take so long. So maybe they're doing something like that. Maybe they're creating some sort of beacon. If you were to take our most powerful laser and shine it at our biggest mirror, you could actually outshine the sun. So maybe they're trying to do something like that and signal us. Maybe they're even using gravitational lensing to signal us. The ideas are, of course, infinite, because we don't know what we don't know. But these are some of the ideas that we think, if we're looking for an optical SETI signal, it could be one of these things. So this is what we could detect, but how do we do it? That's where LaserSETI comes in. So we're basically doing SETI, looking for laser pulses. Now, what is LaserSETI? At the end of the day, it's an all-the-time, all-sky optical survey. We're looking for SETI signals across the entire sky. The goal of this project is a distributed global network. And the idea, again, is to search for extraterrestrial laser pulses. So really quick pulses that may only be there for a second. And we have to scan the entire sky, because if we're going to find extraterrestrial intelligence, we don't know when that's going to happen or where. So we have to be looking at the sky all of the time. And when I say extraterrestrial laser pulses, I don't necessarily mean from aliens. It could just be outside of our solar system. That's what we're looking for. Laser pulses outside of our solar system. Because we need a global network, these instruments have to be pretty compact so that we can ship them different places, and they have to be pretty cheap, which is a really cool part of this project. It actually started with an Indiegogo campaign, so it was all crowdfunded, and it's using all commercial off-the-shelf parts except for two things, which is the diffraction grating and the housing for the instruments, which I'll get to in a second. But yeah, those things are the things that will allow us to build this global network. And these are the instruments. Does this work? Oh, I have a laser pointer for my LaserSETI presentation. That's pretty awesome. Has anybody seen the movie Short Circuit from 1986? That's more hands than I thought. Thank you so much, friends. This instrument, I'm sorry, but it definitely looks like the robot Johnny 5, which gives me an emotional attachment to them. So I'm glad that you all can see what I see, because everyone usually thinks I'm crazy as I talk about aliens. Who is LaserSETI? I told you what LaserSETI was. This is who LaserSETI is. It's a ton of people, a lot of volunteers from all around the world, wherever we install these telescopes. So you'll see the famous Franck Marchis. He just spoke, but he's also the project manager for LaserSETI, and he's taking a picture now of himself on my slide. I love it. I caught that. This is the PI, Elliot Gillum, and this is all of the people that it takes to make these things possible, to install these telescopes, or these instruments all around the world. Different volunteers from astronomical societies, from observatories. Richard Factor, we put one on top of his house. He helped us. It's a worldwide network requires worldwide collaboration, and that's what we're trying to build here. So how does it work? It's a great question. I'm glad you asked. The idea is that we're looking for laser pulses from outside of the solar system. Let me check my time. Okay. The way, or the reason that that's important is because there's no optical narrowband sources, so i.e. a laser, that can't be created by any astrophysical processes that we currently know of. So if we detect something, it could be from extraterrestrials, or it could be new science, which would be just as interesting. So the idea here is not, oh, we're gonna find aliens, but if something does happen, we'll be able to catch it and we'll be able to investigate it. What we do, let me explain really quickly how these instruments work, is we use something called slitless spectroscopy. It's a tongue twister, but we separate incoming light into its components. So this idea is that anything natural, for instance a star, is going to emit light in all different wavelengths of the visible and electromagnetic spectrum. However, a laser pulse, a narrow-band signal, only emits in that one wavelength. So what we do with slitless spectroscopy, we pass the light through a diffraction grating, which separates the light into all of its components. So if you have light from a star, you're going to see all of the components of that light that the star is emitting. But For a laser, you'll only see a small dot because it's only emitting in that one wavelength. So you can see here, these are examples of what a star may look like from our instruments, and then a monochromatic pulse, that narrowband signal, would look very different. So when we see something like that, that's the kind of thing that we're looking for. And this is just to show you all of the different off-the-shelf parts and how cool it is that we can actually build a SETI instrument with off-the-shelf components. Now I told you who, told you what, I told you how. So let's see how it works. Let's see if this will play. I don't know. There we go. Oh, I just wanted to show you. Inside the instrument, this is a schematic of what it looks like. So you saw those two eyes. This is what one of the eyes is. It's basically a diffraction grating that breaks the light into the components. Then there's a lens on top of essentially a camera at the very bottom. And then there are two of these in each instrument, and there are multiple instruments per observatory so that we can check what we're seeing if we get a signal. And here's some specs of the instruments if you can actually read that. One of the really cool things about LaserSETI is that the field of view is incredibly wide. This is necessary for an all-sky survey that we're aiming for. So for example, the small unistellar telescopes that you saw outside are fantastic. Oh, and there's one right here that I missed. These are fantastic, used for an entirely different thing. The field of view on these, meaning what portion of the sky that they actually see, is less than a degree on either side. The LaserSETI instruments see their field of view is 75 degrees in diameter. So they're looking at huge swaths of the sky at any given time so that if there is a laser pulse, we'll be able to see it. We're not limited by our field of view. We also did a little thought experiment here. Frank helped with this. Actually, Frank did it. I can't take any credit for that. But we were thinking about, okay, if we were to receive a laser pulse, or an extraterrestrial civilization was sending one, how far could we detect that out? So we were thinking about the laser that Breakthrough Starshot was proposing, 100 gigawatt laser, proposing or assuming that it's also in a wavelength that we can see. If that same laser was to be sent by some sort of extraterrestrial civilization, we would be able to detect it out to 5 light years away. And of course, if they have stronger lasers, we'd be able to detect signals from even farther. So that's just to give you an idea of what we're working with here. Now, the current status of LaserSETI, like I said, it's supposed to be a worldwide global network, and it will be. We're well on our way to doing that. Right now, there are 4 stations, each comprising of 2 to 3 instruments each. One in Hawaii at Haleakala, in Sonoma County, California, in Sedona, Arizona, and also one in Puerto Rico that we just installed a month and a half ago, 5 weeks ago, so it's brand new, yeah. Super exciting, and this is actually a time lapse of day 2 of the installation just to show you what goes into this process. You will see Frank actually working. You will see me largely standing around, pretending to help. It's my superpower, actually. But no, this was a fantastic installation process. It gets smoother every time that we do this and we learn this process, and we were helped out by the Department of Marine Sciences, the University of Puerto Rico at Mayagüez. It's very long, but they were very helpful, and the entire observatory sits on their roof. So this is the collaboration that I'm talking about is necessary for these global efforts. And this, just to give you a sneak peek, because we're all friends here, was the first light of one of the instruments. We call that one MAG 3. So this is the interface that our PI Elliot Gillum was using to take pictures, the very first pictures, to make sure that the instruments were online, and in order to focus them and see if there was anything in the way. But this is it. This is first light of our Puerto Rico observatory. Now, I've told you where LaserSETI stands right now. What is the future of this network? We are going to expand. So as you can see, this is, oh, no, don't do that. This is a map basically showing the field of view of all of the current and proposed observatories. Even though there are 4 observatories, that's 9 instruments, and we're proposing about 9 more, you won't see 18 field of view on here individually. It's because some of them need to overlap. So each observatory actually overlaps with another observatory somewhere else in the world. And that is necessary because if we see a signal, we want to be able to confirm it and validate the fact that it wasn't just an artifact in the camera or from that particular location. We want to be able to say that it's real, and we want to be able to locate it in the sky. And to do that, we need overlapping coverage from multiple different observatories. Right now, with the addition of our Puerto Rico installation, we can see, or we survey about 40% of the sky. And with these additional proposed observatories, we'll be observing about 60 to 70%. So we're well on our way to world domination. Cue the Pinky and the Brain music. Another aspect of the future of LaserSETI is why we're all here today, is that citizen science aspect of sharing data with the community. So right now, data is currently being stored on site on the actual instruments. It's then uploaded to S3 servers and downloaded to a private server after that. And that's just because the pipeline was built that way. Pipeline is basically a giant set of code that is processing all of this data, and this is where it lives. But our next move is to basically store all of the data with Akave, which is what Frank was talking about earlier, this decentralized storage. And that's really, really helpful in this field of astronomy, because right now we have servers like Amazon, Google Cloud servers. These are centralized storage companies. So basically there's one place where your server is located, your data is stored there. If something happens, you are not in a good place. No single point of failures are not good. But at the same time, it's hard with these servers because if you want to store large amounts of data from a long time ago, that data goes into cold storage, basically, where it takes a lot of money, a lot of time to get it out. And that's not really sustainable if we want to share all of this data with the world and be able to disseminate this data so that people can use it for different projects no matter when it was taken. Now, or with this centralized way of storing information, we also don't really get that information verified. We have no way of saying, yes, this data has not been tampered with. So by moving to Akave storage, to a decentralized platform, that data is shared across multiple different nodes that store it. It's cheaper to get out data that is a little bit older so that people can use it for multiple different purposes. And we'll be able to more easily share that data with the community and involve everybody else. Another aspect of the future of LaserSETI is using it for additional science. So even though we're looking for laser pulses, there's a lot more that LaserSETI can do, especially because it has such a wide field of view. We're observing so much of the sky, and we have a really, really nice time resolution. So we can see things that are really quick, and we're not limited by small fields of view. So this is what you'll see is called a sky flash. I need you to look, like right here is where you're gonna see this. Did y'all see that really bright point of light? So that is actually what we think is called what we think is a meteor. It's called a sky flash. We think that this happens when a meteor is actually too dim to be seen as it typically would, which is from the side when you see that nice tail. But if you have that meteor traveling directly along your line of sight, you see it get a lot brighter, and you're able to see it from this particular point of view, whereas you wouldn't anywhere else. So that's the kind of thing that we can catch by looking at all the sky all the time. And we can have this data stored on a Kave cloud for anybody to use, so that we're not just looking for ET, we're not missing out on the potential other science that could be done. So meteors, transient events, Frank was talking about Rubin earlier, and even space debris re-entry. These are all things that will be possible with LaserSETI looking at the sky all the time. Now, to the point of the talk, which is what everybody usually wants to know when I'm talking about LaserSETI, is have you found anything yet? The answer is no. But that's okay, because the search has not been going on in this form and fashion for a very long time now. Let me tell you how we search, though, and how we verify candidates. We do have a few candidates that we have received over the last couple years. I think there were about 7 that were our top-level candidates. They turned out to be false positives. But what we do with the data each night, this is very simple. I took an hour-long conversation with our PI and boiled it down to this. So when we see a potential signal, when our pipeline sees a potential signal, it asks, is it bright? Is it brighter than the surroundings? And then it asks, does it move like a star? If it's not moving like a star, it's probably an airplane. And after we decide that it's bright enough and it's moving like some sort of object that we would expect not on Earth, we can see, does it look the same in multiple fields of view, in multiple instruments? And if that is the case, then you have yourself the highest level candidate. Like I said, we have, I think, about 7 of those now, and we basically save all of that data. All of the candidates that we've ever received are stored on our server so that we can share that with the outside world and follow up those candidate observations. So I'm going to show you and I'm almost done. Let me show you what a candidate looks like. I know this does not look like the typical picture that you would think. Our telescopes are capable of doing that, but we're using something called time delay integration here in order to read out the information that's stored on the camera. And the reason that we do that is because our cameras do not track the sky. The instrument is stable, it's looking at the sky, it doesn't move, it doesn't track as the sky moves over the course of the night. So we have to use this special technique that accounts for that, and that's why what you're seeing here isn't a typical picture. This was, again, the most interesting recent intriguing candidate, but it turned out to be a false positive. It actually looks like all of the other stars in the field of view. So this is the kind of thing that we come across a lot. But what's really cool about the way that these work is this information is stored. We have these records for ad infinitum, which is not the way that you use that Latin term, but I'm going to pretend that it was correct. So at the end of the day, what we're all here for is to figure out how we can get involved in science and how we can share science broadly and without the barriers that the current scientific ecosystem kind of has. And that's what we're on our way to do, is to help you get involved. So some of the ways that you can get involved right now are, if you have a location that you think would be a great idea for an observatory, share that with us. We're working on essentially making our little LaserSETI robot instruments into smaller, more compact, more what's the word I'm looking for? Easier to transport. We're trying to make them more accessible. So our idea is that we'll be able to have more and more of these around the world. So if you have an idea for an observatory location, let us know. Once our data is public, like I said, we plan to do that. You can participate in the follow-up inspect candidate events. You'll be able to use that data for other science cases like meteors or transient events like I was talking about earlier. You could even feed that data into an AI and help us figure out how to improve our pipeline that is looking for these candidate events. So, in conclusion, this is Johnny 5. This is the robot I was talking about earlier. In conclusion, for the future of LaserSETI, we're going to put little cowboy hats on all of our instruments. I'm just kidding, absolutely not. But in conclusion, to summarize this grand search that we're trying to do, LaserSETI is an all sky, all the time optical SETI survey. And its aim is to decentralize its data and to help you get involved as well. We haven't yet found aliens, but that's not all that LaserSETI can do. There's a lot of additional science that can be done. And right now we have 4 different observatories around the US and Puerto Rico, and we will be expanding, hopefully next into Saudi Arabia, Canary Islands, and Bhutan. So we're growing, and you can follow us, please do. You can stay in contact with me. You can follow us with our updates on our website, laserseti.net, or on different social media platforms. Yeah, I think that that's all I have to say, and I hope that you join the search with us. Thanks.
All right, any questions for Lauren? Any alien questions? Guys, this is your chance.
Yeah, my only question is, when do you plan on having data accessible by the public?
That's a great question. I do not know. I cannot answer that. It is currently a work in process. Oh, he can? 3 months. That comes from the big boss. So if it doesn't happen, don't come for me, come for him. And again, that Akave cloud storage that I was talking about, that's currently in process for our most recently installed observatory in Puerto Rico. So we've already started that integration. So yeah, it should be soon. Thank you, that was a great question.
Hi, so I was wondering what type of, I don't know if it's like research or decision making goes into, I guess, where you're going to be building the observatories. Like, what do you do to kind of look into, you know, protecting the biodiversity of these places that you're wanting to expand into, so that we can both have the observatory and also, you know, protect any wildlife and again, like keeping biodiversity still in existence?
Absolutely, that is a great question. Thank you so much for asking. In Puerto Rico, we actually installed on a small islet off the southern coast called Mayaguez, I'm sorry, mispronounced that. But there were a ton of iguanas. It was incredible. However, the installation process is not incredibly invasive. We're not, or currently have not, installed any observatories in places that were already naturally protected. They're all on rooftops. They're all already on buildings. And the most invasive part of the process involves bringing the instruments up to the roof. And it's only a 2-day process, luckily. So we haven't had to think about that too much so far, because we usually work with local populations that would tell us if what we're doing is particularly invasive, but that's really good for us to think about in the future. So thank you for asking that. Anything else?
Okay. One more round of applause, please, for our speaker.
Thank you all so much.